Hello and welcome to another lecture in the course. So we're moving on to Laplace transform. It's section 6.1 in the book. And understand that this means we're jumping a little bit, but there's a uh, more common topic that's taught in this sort of classes. So let's cover it first before eventually we at some point get to chapter 3. So we're kind of skipping to chapter 6. Anyway, so the book, you can get it free online, or you can actually buy a paperback, or get a PDF, or view it on the web at this address. It's also in the description. All right, so let's get on with Laplace transform, and how are we going to use it for differential equations. So it's first part of 6.1. All right, so uh, solving differential equations is hard, as you've seen by now. We've only solved some really simple ones too. And it would be a lot easier if we just had equations but no derivatives, right? If we just had these, let's call them algebraic equations. There's no derivatives whatsoever. There's just the different variables are multiplied, added, and so on. And then we have an equation, and then it's just algebra to solve. So that would be nice. That's what Laplace transform does, right? So what Laplace transform does, it takes the differential equation, and what it does, it transforms it into an algebraic equation. Now in different variables, but we're going to get an algebraic equation where there's no derivatives whatsoever, and we just solve that. That's easy. We know how, like you learned that in high school and even in primary school, how to solve algebraic equations. Find x. So we know that. So that's really easy to find the algebraic solution. Now, that's, as I said, in different variables. So then you need to invert this Laplace transform. And let's not for the moment worry about exactly what it is yet. Well, we will worry about what it is in a little bit. So you have to invert this process, right? The one that we did over here. And then you get a solution to this differential equation, right? So instead of doing this hard bit over here, trying to go directly from the differential equation to the solution of the differential equation, we seem to go a little bit sort of around, right? So do a bunch of stuff, but all of these steps are actually relatively easy compared to the hard bit over here, or sometimes. I mean, of course, it depends on on the exact um, on the exact context, right, where this appears. But that's sort of the idea. We want to bypass this hard bit with a bunch of easy bits, but we're going a little bit around, right? All right. Now, there's other applications for Laplace. Actually, I mean, in some sense, they're not other applications. They're all kind of connected to the same idea. But it's used in electrical circuits analysis, NMR spectroscopy, signal processing, etc., etc. It has lots of applications in real life, and in various of your in various other classes that you might take as well. So it appears all over the place, not just for in differential equations in the way that we're going to apply it. Now it's similar to Fourier transform, which is same thing as Fourier series. I mean, it might seem a little different. In Fourier series, you have a series instead of an integral, but it's just a big sum. So the Fourier transform and Fourier series, it's kind of the same, from the same circle of ideas anyway. So, and this is similar. So basically, what it does is it takes a function, and you can think of it as a signal. So it's some function of time t, right? So there's some signal in time as it's coming in, and it takes that signal and it transfers it to a different function in the frequency domain. Now, I put this frequency in quotes because, well, it's not really here it's not the frequency that you really think of as frequency. It's kind of the complex version in here. It's really going to be the imaginary part of the frequency, or the decay part of the frequency. Let's not worry too much about that. We're still going to call it frequency, even though it's not really going to look like frequency in terms of like cycles per second kind of thing, right? Anyway, but it basically takes a function of t and gives us another function of s, right? Which is going to look different, but they're related, right? For every function of t, there's a function of s, or at least for every function where this is going to be defined, right? So it's this black box, and into the black box, I throw a function of t, and out comes a function of s. And we're also going to be able to invert this process, right? So once I know the right function, capital F, I'm going to get this little function little f, right? So we can go back and forth, right? I mean, we need to understand these two arrows here, basically, right? And so it's, just a bit of notation. I guess I've just used it here. Is we'll use capital letters for the transform of the function, where we use lowercase levels for the function itself. It is fairly standard. Not everywhere. It's like, for Fourier transform, which is kind of the same thing. A lot of times you use hats. So you have f and f hat. Same sort of idea, right? It's a different function. It's a function of a different variable, completely, and it means something different, but they're related by this formula, right? Well, it doesn't give you the formula to how to compute it, but there's going to be a formula for this. All right. So that's the idea. So how do we solve, or how does this apply to the differential equations? And again, we haven't yet defined the Laplace transform. We'll do it later. But how are we gonna use this, right? And the way in this entire chapter, we really want to think of and we have an equation like this, right? So it's an equation in x, m, c, and k are some constants, and there's some right-hand side f, right? And so we're trying to solve for x. So what we're going to do is we're basically usually going to think of the left-hand side as being kind of fixed. That's sort of corresponding to the setup, to our to our device that we're analyzing, whatever it is, circuit or a mass spring thing or whatever. And the right-hand side we're going to think of as the input, and the solution x we're going to think of as the output, right? So you can think of this equation as again, this sort of black box that eats an input and gives you an output, right? So it eats f of t and gives you x of t, right? That's the way that we're gonna, and that's gonna make a lot more sense as we move on. So, and we'll take t equals 0 as our starting point. That's gonna make the way that we define Laplace transform, that's the convenient starting point. If you have some, if your signal is given in some different time, translate everything and make it be t equals 0. So we're gonna think of t equals 0 as the starting point. That's where everything starts, and we're only gonna think of positive time. So for negative time, we can think of all of our functions just being 0 for negative time, or just not existing whatsoever. So we really are only interested in positive t, or non-negative. I guess we're including t equals 0, but just from t equals 0 onwards. We don't care about history, right? We're ignoring history, despite what the historians tell us to do, right? We ignore history. We're just looking for, at the future, right? All right. So in the, in the sectional mass spring setup, right? The F was the external force, and the X is the position of the mass. So the external force is the input to the problem, and X, the position of the mass, that's the output, right? Or an RLC circuit. That was another one of these examples, right? And in that case, the change in voltage from the source, right? That's the input, right? That's the F, and the X in that case, I guess we wrote it as capital I, but that was the current in the circuit, and that's the output, right? Figuring out what the circuit does, right? Given some input, right? Given some input signal, F. All right. So what's going to be the solution procedure? And I guess we outlined it in the previous diagram. But basically, what we do is we transform the input F into we hit it with the Laplace transform, we get capital F. We do the same thing with the equation, and we're going to get an equation in just capital X, which is the transform of little x, right? And capital F, which is the transform of little f, right? So we get this equation, and it doesn't have any derivatives. So we solve that by algebra. We find capital X. Now that's x of s, and we're going to invert the transform. Once we know what's the formula for x of s is, then we can do an inverse transform and find little x of t, which is really what we're interested in, right? We're given this f of t, that's where we start, and we want this x of t, right? That's what we want. We don't really care about this f of s and x of s. They're just a way to get from f of t to x of t, right? All right. So finally let's define what the Laplace transform is, right? So I've been sort of yapping about it for a while. So let's look at what it actually is. So given any function f of t, well, one where this is going to be defined, we compute this integral where s is some, for every s, or for every s in some range. Generally, we're going to look at s bigger than some number. So for every s bigger than, let's say, 0, so positive s maybe, sometimes maybe bigger than 1, sometimes bigger than a million, but it's just going to be every s in some range. But you fix that s and you compute this integral over here. And because we do it, you're going to get a different thing for different s. It's a function of s, right? So that's our capital F of s, right? So we have this formula, right? The Laplace transform is the way that we're writing the Laplace transform. Well, either like this or like this, depending on what's useful. Then we just compute this formula. So let's look at some examples. So suppose that this function is just 1. And again, we're really interested in this function only from 0 onwards, right? So I mean, that's where this integral is defined, right? So we write down what it is that we're supposed to compute. That's capital F of s, is this thing. You will notice that it's not going to be constant. Even though we start with a constant, we're not going to get a constant. We're going to get some function of s. So, all right, well, let's just compute this. Let's write it like this. Now, remember that if we have this infinity, this really isn't like, we're not plugging infinity into anything, right? I mean, it is a limit, right? It is this limit. This is really what it is, right? I mean, we solve this. I mean, this is kind of shorthand for this thing, right? We're taking some sort of a limit as h goes to infinity. I mean, infinity is not a number that you can just plug into something, right? So we have this limit, and so we want to compute it. like what is this, right? I mean, that's this thing, right? So um, so over here, I mean, just this second bit, that's easy. We know how to handle. Well, there's no h. We don't have to handle it. It's done, right? So really, the thing is out here. The h is only out here. Now, if s is positive, then as h goes to infinity, minus sh goes to minus infinity. So e to minus sh will go to 0, right? And so we get 1 over s, right? Notice that this minus s, this minus and minus cancel out, right? So we get 1 over s. And of course, the limit only existed for s bigger than 0. So really, this function is only defined for s bigger than 0. All right. But that's, as I said, that's what we're looking at. So you can see that the Laplace transform of the constant function 1, right? Which is, again, a function of t. Just for every t, just go 1, is 1 over s, which is not constant, right? Let's do another example. Let's do e to the minus at, right? For some a, for some number a, right? So we take a look at e to the minus at, and we hit it with the formula that we just we just said that's what the Laplace transform is, right? So we just basically stick in, for that f of t, we stick in e to the at, right? That's where we're putting it, and now we just compute this, right? So we use laws of exponents. It just looks like this, and then the computation is basically the same thing, except instead of s, I have s plus a, right? It's essentially the only thing that's different here. So what I get is 1 over s plus a, right? Again, I need s plus a to be positive. That means that s is bigger than minus a. So if a is, let's say, 5, right? So I have e to the minus 5t, then then s should be bigger than minus 5. If a is, let's say, minus 5, so it's e to the 5t, right? Then s should be bigger than 5. It's not even like s equals 0 or close to 0 wouldn't be good enough. You'd need it to be bigger than 5, right? But once s is large enough, then this is defined, and it's 1 over s plus a. All right. So okay. So now we know how to transform 1 and the exponential. How about t? That's also a useful function, right? We're like 1, okay, t. We're eventually gonna get to t squared, t to the t cubed, and so on, right? Sine of t, cosine of t, but yeah, let's just keep going. I'm gonna leave most of these as sort of exercise for you, but let's do t, right? All right, so I plug in t into this formula, right? Then we do integration by parts, because how do you integrate something like this? Well, you want to differentiate t and anti-differentiate e to the minus st, and that's what happens here, right? And again, we're assuming that s is bigger than 0, so that this is e to the minus st. So that's gonna go. If we're taking this limit out here, right? That limit goes to 0, right? Same thing out here, right? So, all right. So if you do that, right, you will notice that that you get 1 over s, and then this is basically the same as the limit that we did before. That was 1 over s, but now I'm also multiplying by 1 over s, so I had 1 over s squared, right? So that's the Laplace transform of t. Laplace transform of t is 1 over s squared. So you can see they're different looking functions, right? Very, very different, right? I mean, t is this very nice thing, 1 over s squared, right? I mean, it blows up as s goes to 0, but yeah, again, we're just assuming that s is positive. But they are different looking functions anyway. All right. Now, the next one that's going to be quite useful is so-called Heaviside function, or the unit step function. It's a function that's basically, it's going to be zero until zero, right? Or maybe I should use a sharper pen, right? So it's zero, all the way up to zero, and then at uh, at once t becomes zero, the function just becomes one, and then so this is this is where one on the vertical axis, right? So it's just zero, 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 and then at zero it jumps to one, and then keeps going as one forever, right? So it's a very simple very simple function. Now, when I first heard this, um, I always thought it's called Heaviside function because it's heavy on one side, right? It's kind of heavy on this side and nothing on this side. But Heaviside is actually a name of somebody, right? It's named for this guy Heaviside. So it's not it's just by chance that it's heavy on one side. All right. Now this function a lot of times here, this in this setting, it wouldn't be so useful. So a lot of times we shift it. That's how it's really useful. So we can shift it by some a, right? And if you shift it by some a, basically, these zeros becomes a's, right? So it's u t minus a, right? So it's this function that is zero all the way up to a, whatever a is, and then it jumps to one and then is one from then onwards, right? So that's it's usually a lot more useful formulation. You usually wants to move this thing around in a bunch of different ways. We'll see how that comes up a bit later, right? All right. So assume again that s is positive, and let's suppose that a is bigger than or equal to zero. I mean, we probably as the Heaviside function could be useful for a less than zero, but as far as Laplace is concerned, we don't care about what happens for negative t, right? So we really only care for t bigger than or equal to zero, and so shifting it leftwards wouldn't really be useful. We just get the function one, right? I mean, even this guy just on its own, if a is zero, right? So it's just have u of t, just the standard Heaviside function. As far as the Laplace transform is concerned, it is the same as the function one, right? Because we're only looking at t bigger than or equal to zero, and when t is bigger than or equal to zero, that function is one, right? So that's where this that's where this restriction to a bigger than or equal to zero comes in. It's as far as the Laplace transform is concerned, we don't care about this function when it's shifted leftward. We're only going to shift it rightward in a bunch of different ways. Anyway, so let's do the Laplace transform of this rather simple function. So again, I just plug it into the formula, and now you notice that this thing is zero until a, and then it's one. So if I'm integrating zero from zero to a, and then I'm just integrating e to the minus st from a to infinity, right? So it's almost the same thing, except I'm starting at a over here. So I don't quite get the 1 over s, but I get basically just plugging in for the letting t equals a in here, right? So I'm going to have e to the minus as, right? Because that's what I get from this, right? So in the numerator, so I have e to the minus as over s, and you will notice that if a is zero, this really is the same thing as just the constant one, because then e to the minus zero times s, that whole thing is one, so it's 1 over s is the Laplace transform of u of t, right? So again, it wouldn't be very useful, in this formulation, but that's what u is. But u of t minus a, that's really what we're going to be interested in, right? And then it's this thing. All right. So now we did a bunch of examples. So here's a useful table, right? So we have if we have one or actually any constant, right? You could have so any constant over so any if you start with any constant, you take the Laplace transform, you have that constant over s. Start with a t, we said it was 1 over s squared. You do the same thing as t squared, you will need to do integration by parts twice. You will get 2 over s cubed. If you do it, if the function is t cubed, then you have to do integration by parts another time, and you will find that it's 6 over s to the fourth. And in fact, what you'll find is that if you look at t to the n for any n, right, for any positive power n, 1, 2, 3, 4, 5, 6, 7, 8, 9, whatever, right, then you get this this formula, right? And basically, it's if n is 5, you'll need to do what 6 integration by parts, I guess. Anyway, it's you can sort of figure out what this formula is. Like, you wouldn't have to just always keep doing it. I mean, if you recall what we did in the in the previous thing, I mean, when it was t, after one integration by parts, you would recognize the formula, in there for the, in that case for the constant 1. So, in this case, you'll recognize the formula for t to the n minus 1. Anyway, so, that's what it is, right? E to the minus at, we did that. It's 1 over s plus a. If you have sine of omega t for any constant omega, you get this thing. If you have cosine of omega t, you get this thing. If you have sinh sorry, so hyperbolic sine of omega t, you get this. So very similar. Notice the difference is the sine in the denominator. Cosh, again, very similar to cosine. Again, just the difference in the sine in the denominator. And we did the Heaviside function. That was this thing, right? So here is the sort of a basic table. And as far as we're going to be concerned, for all the homework and whatever in the book, it's this should be good enough. There's a longer list of transforms in the back of the book. If you want a bigger table, then you can probably find much bigger tables online as well. But for the basic computations that we'll be doing, this is going to be good enough. And actually, this is the way that we're gonna most of the time, at least in this class, but in practical applications, that's basically what most most people will do. Is instead of applying the formula directly, you apply the formula directly if you're starting with some function that is not in any table that you can find. But if it is in some table, you probably look it up in a table, right? And we'll see that putting things together with linearity, this will be good enough for most things. All right, so this is an exercise. Verify the tables. Like, finish these computations, right? Do this, right? These things are, we haven't looked at yet, but it's just calculus. All right. Now, I mentioned linearity, right? So why is this going to be linear? It's because the integral is linear. So if c is a constant and we have constant times little f, and we plug that in, that c can just go outside, right? And we get this thing, which is just the transform of f, right? So you can see that the Laplace transform of c times f is c times the Laplace transform of f. And that's, you can also do addition. So you really have just complete linearity. So if A and B are constants, A times F plus B times G, and I take the Laplace transform of that, it's the same as taking A times Laplace transform of F plus B times Laplace transform of G. That means that previous table is actually, that gets, a lot of functions. For example, it gets all the polynomials, or, if you add any linear combination, if you add any, sines, cosines, and exponentials, hyperbolic sines, hyperbolic cosines, stuff like that. So, for example, if I have the Laplace transform of 2 plus 9t plus sine of 2t plus 5 e to the minus 2t, then I, I could use this, I could use this this expression, so linearity, to write it like this. So I could have Laplace of 2, that could actually be 2 times Laplace of 1, right? It would be the same thing, plus 9 times Laplace of t, plus Laplace of sine of 2t, plus 5 Laplace of e to the minus 2t. And so we can see that I get the 2 over s for this thing, plus 9 times 1 over s squared from this thing, then plus 2 s squared plus 4, right? So this 2 comes from the fact that this is a sine, there was an omega on top, and then plus 5 times the Laplace transform of e to the minus 2t, so it's 5 times 1 over s plus 2, right? So we can now use the table to basically transform a whole bunch of functions with that just small table and linearity. All right. Now, one word of caution. It would be sort of nice if it were true, but it's not, right? This is not true, right? It's not true that if I have a product, just this algebraic product of functions, it's going to be the product of the transform is the transform. That's just not true. So yeah, so just don't do that. This is not true. So it would be nice maybe, but it's not true. Now, not all functions have a transform, right? So you can't just plug in any little f. It only works for a lot of functions, but not everything. So, for example, 1 over t, it doesn't work because if you have 1 over t, the sort of integral just doesn't work, right? Because you're gonna even if you write it as an improper integral, it won't exist. So it's there's that that blow up at t equals 0. Now it's even worse with something like tan of t that blows up not just at 0 but at a bunch of places. Or it could blow up really fast at infinity, like e to the t squared also doesn't have a Laplace transform because e to the t squared blows up too fast as t goes to infinity. So not everything has Laplace transform, but a lot of times the types of functions that would come up when doing some sort of a signal, a realistic signal, actually those guys are going to be perfectly fine, and you don't really need, even continuity is not really necessary. You can have easily jump discontinuities, and we'll talk a little bit more about that next time. We'll give a sort of a large enough class that has Laplace transforms. All right, so basically more on Laplace transform next time. All right, see you then.